Hi, in this video of Inkpot we shall study about Fourier coefficients. These are quite important and a lot of theory has been developed on Fourier coefficients. These are used in several applications. Right now we shall be dealing with the results and examples related to inner product spaces. So let's start with the definition. If beta is an orthonormal subset, we usually take a finite subset of an inner product space V and X is a vector in V. Then we define the Fourier coefficient of X relative to beta to be the scalars inner product X with Y, where Y is any element of beta. So the main motivation behind these Fourier coefficients came from the study of scalars Cn, where Cn was 1 by 2 pi 0 to 2 pi ft e to the power minus int dt for any function f. So basically this Cn was equal to inner product of f with fn, where fn was e to the power minus e to the power int. So because fn is e to the power int and we have seen this inner product, this is equal to 1 by 2 pi 0 to 2 pi ft fnt bar, which is e to the power minus int dt. So these Cn's were called the nth Fourier coefficients, and there was a representation of a function in terms of these coefficients which was possible, and from that this definition of Fourier coefficients of an element in an inner product space has been taken. So now let's see the representation of the vector in terms of the Fourier coefficients. So the theorem says that if V is a non-zero finite dimensional inner product space, then V has an orthonormal basis beta, and if beta consists of v1, v2 and so on till vn, and x is a vector in V, then we can write x as summation I varying from 1 to n inner product of x with vi times vi. So let's see the proof. Basically, first of all, we have to show that for any non-zero finite dimensional inner product space, there always exists an orthonormal basis. So because V is non-zero finite dimensional inner product space, so V has an ordered basis, let's say beta naught. So we have beta naught. Now by applying Gram-Smith orthogonalization process, we can obtain an orthogonal set beta dash, let's say consisting of non-zero vectors such that span of beta dash, this is equal to span of beta naught. Now because beta naught was an ordered basis for V, so span of beta naught is nothing but V. So now by normalizing, we can normalize each vector in beta dash. So we can, by normalizing each vector in beta dash, we get an orthonormal set beta such that span of beta, this is equal to V. So now beta is an orthonormal set and it spans V, and because beta is an orthonormal set, so we have done a corollary which says that beta is linearly independent. Any orthonormal set is linearly independent, so beta is linearly independent, and this implies that beta is an orthonormal basis for V. So now let beta is equal to v1, v2 till vn. So we already know that if we have an orthonormal set S and y is a vector in span of S, then y has a representation summation inner product y vi I varying from 1 to n, where this S consists of vi I varying from 1 to n. Okay, so now beta consists of these vectors and beta is orthonormal. Beta is an orthonormal set. So if x belongs to V, then x is nothing but summation inner product x vi I varying from 1 to n, and hence the theorem is proved. Now let's see a corollary to this theorem. So as a corollary we have that if V is a finite dimensional inner product space and beta is an orthonormal basis consisting of V1, V2 and so on till Vn, and T is a linear operator on V with matrix representation matrix A, then for any I and j, the ijth entry of A is given by inner product of T Vj with Vi. So let's see the proof. So by theorem, what do we have? We can write T Vj as summation I varying from 1 to n inner product of T Vj inner product with Vi and Vi. So now Aij is a matrix representation of T with respect to beta, right? So the ijth entry of A would be what? It would be the coefficient of ith coefficient of T Vj, like ith coefficient in the representation of T Vj as the linear combination of basis vectors, right? So here we have represented T Vj as the linear combination of the basis vectors Vi. So this is basically equal to T Vj inner product with V1 times V1 plus T Vj inner product V2 and so on till T Vj inner product with Vn and Vn. So what would be the ith coefficient? Ith coefficient would be Aij is the ith coefficient, and this is equal to inner product T Vj inner product with Vi. That's it. So this was what was required, and hence we know the ijth entry of this matrix representation. Let's see some examples. So we are taking the space H to be the space of all continuous complex valued functions defined on the closed interval 0 to pi, and S to be the subset of H consisting of the vectors functions e power I and t where n belongs to Z. Then S is an orthonormal subset of H, has the inner product of any function. Let's take e to the power I n t with e to the power I m t. This is equal to 1 by 2 pi 0 to 2 pi e power I n t, the conjugate of e power I m t, that is e power minus I m t dt. This inner product we have already defined earlier. So now this is equal to 1 by 2 pi integration 0 to 2 pi e power I n minus m t dt, and this is equal to 1 by 2 pi e to the power I n minus m divided by n minus m, and 0 to 2 pi. So this is defined for n different from m, right? Where m is different from n. So if n is different from n, this is equal to 1 upon 2 pi into e to the power, because this is a periodic function of period 2 pi, so this is 0 in the numerator, so this is equal to 0. So when n is equal to m, we have e to the power I n t e to the power I m t. This is equal to 1 by 2 pi 0 to 2 pi e to the power I n minus n dt from this star, and this is equal to 1 because it is the integration of 1 by 2 pi integration 0 to 2 pi 1 dt, which is 1, and hence this implies S is a orthonormal subset of H. So let's take the function ft to be equal to t, and now we shall find the Fourier coefficients of this function f. So let's find out the Fourier coefficient f with fn. So the nth Fourier coefficient f with fn, this is equal to 1 by 2 pi 0 to 2 pi ft, which is t, into fn bar, which is e power minus int dt, and we can calculate this integration by integration by parts, and this comes out to be minus 1 divided by in, where n is different from 0, and this is equal to pi for n is equal to 0. In the next video, we shall study some important properties of the subsets of an inner product space called orthogonal complement of a subset S.